So in this notebook, I just want to show how Mitiq can be used with Qiskit quantum programs. So these are the three main sections of the notebook. I will first show how to compute a noisy expectation value without mitigation, so without Mitiq at all. Then I will try to apply zero noise extrapolation. And finally, if we have time, probabilistic error cancellation. So if you're running the notebook, you first need to install Qiskit and Mitiq, which can be done by executing this code cell. We filter some warnings, and we just define the circuit of interest. In this case, since it's just an example, what we do, you don't have to look at the details of the code, but it's just a way to generate a randomized benchmarking circuit of 2000 gates, more or less, 2 qubit and single gates, and also 2 qubit gates. So it's a lot of control nodes, which are the most noisy gates of the circuit. So this circuit is very long, 2000 gates, and so we expect it to be sensitive to noise if we execute it on a noisy backend. And why we use randomized benchmarking circuit? Because they are built in such a way that the ideal result is the identity operation. So we know what is the final state in principle, which is the 0-0 state. And so we can check if how strong is the effect of the noise and how good is the effect of error mitigation. So first, let's try to execute the circuit with an ideal backend. So we set the number of shots, 10 to the 5. We initialize a simulator. We append the measurements to the circuit, and we get the counts. And from the counts, we estimate the expectation value of an observable. In this case, the meaningful observable is the projector on the 0-0 state, which for a randomized benchmarking circuit should be 1. And so if we run this cell, indeed we get 1, because there is no noise in the execution. So now, if we want to check what happens with noise, we just need to replace this ideal backend with a real backend, or at least with a simulation of a noisy backend. So we basically copy the same instructions, but instead of initializing the ideal backend, in this case, you could do the following. You could initialize a real IBM device if you have an IBM account, and if you want to run this on hardware, but I suggest you to first start with a simulator because things are much easier. And in this case, we import from Qiskit a classical clone of the real device. It is called fake lim. And by the way, the device is a 4-qubit device where it is important that we are going to use just the first 2 qubits because our randomized benchmarking circuit is a 2-qubit circuit. So apart from this, the code is exactly like before, and what we get is that the final expectation value is 0.75. So there is some fluctuations, but more or less that's the result. And it's not 1, exactly because of the noise. So the aim of, in this case of error mitigation, is to try to reduce the noise such that we get an expectation value which is closer to the ideal one, closer to 1. And so we can try to apply Mitiq, and in particular, zero noise extrapolation. So the first thing that you have to do if you want to apply Mitiq is to define an executor, which in the simplest scenario is just a function that takes as input a circuit and returns the expectation value that you want to compute. So in practice, what we need to do is exactly apply the operations that we defined before, the instruction to compute the expectation value, and to wrap them into a function that is called executor. So we just copy exactly the same type of operations, and then you get this noisy expectation value, and you return it as a real number. So once you have this function, you can just run the same experiment as before, but now everything is wrapped inside this executor function. So the reason why we need this executor is that this is used by Mitiq as a black box in order to apply error mitigation techniques. So let me first show really the simplest way to apply error mitigation in a real computation, which is you can import Mitiq, and then you just decorate the executor with, in this case, a zero noise extrapolation decorator. And if you do this, sorry.
Yeah, I was going to ask you why there's two.
The name of the decorator is with the underdash. So if you do this, now you can still use the executor as before, but what happens is that zero noise extrapolation is applied under the hood. And as you can see, you get a better result, which is closer to 1. This is the first thing to notice. And the second thing to notice is that we are actually calling the experiment several times because we are applying zero noise extrapolation. So we are executing 3 different circuits with different depths, which are sensitive to different amount of noise, which are extrapolated by Mitiq. All this happens behind the scenes, so the user doesn't need to care about this. But on the other hand, sometimes you want to play with the details of the extrapolation, and so it is better to check what kind of options you can use.
Which type of extrapolation is, or how do you set the settings on extrapolation?
Yeah. Exactly. So the default one is Richardson extrapolation, and the scale factors are 1, 2, and 3. Just default choice of Mitiq, but you can change this, and I will show this exactly in the next slides. So in the next cells.
And this is global folding?
Well, actually, this is another way of doing exactly the same. Instead of decorating the executor, you can instead call execute with ZNE, and you get exactly the same computation. I'm not doing something different here. I'm just trying to quantify how much the error was reduced. But here it is, yes, the part in which you can choose the noise scaling method and the inference method. So all the noise scaling methods can be found, they are actually represented as functions that take a circuit and gives as output a noise scale circuit. So let's call this function a noise scaling function. And let's import one of these functions from Mitiq. For example, fold global is the one that I've shown you before in the talk. By the way, the default one in Mitiq is fold gates at random, which applies local folding to a random subset of gates. Now, just to change something, we pick fold global. And just to check if it is working well, we get a circuit, and we apply the function, and we get a new circuit with more gates, actually with more or less the double of the gates, because the scale factor is 2. If you take, I don't know, 1.7, approximately you get 1.7 more gates, and so on. That's the noise scaling method. What about the inference method? The default one is Richardson extrapolation. So it can be initialized as a factory object, which is, for example, where it is, Richardson factory, where you can set the scale factors as a list of numbers like 1, 2.7, 3, 5.3, just random numbers at the moment. And once you have this, you can call the function execute with zero noise extrapolation and pass this noise scaling method and extrapolation method as arguments. And what you get again is an extrapolation, which you can also analyze later by looking at the factory object, by looking at the data inside the factory object. For example, you can plot what is happening behind the scenes. For example, in this case, 4 noisy expectation values have been measured and Richardson extrapolation has been applied to get the zero noise limit. And equivalently, you could apply exponential extrapolation and so on. I think this concludes the zero noise extrapolation part. And before I go to PEC, I don't know if there are questions, or otherwise I will proceed.
There are questions about PEC, so keep going.
Okay, good. So to apply PEC, we import the PEC module of Mitiq. And the first thing that we need to know about PEC is that in principle, we have to know the noise model of the system completely. So the full tomography of all the gate set that you are applying. However, a good approximation, not a bad approximation, but a very simple one to apply is to assume that first, the noisy gates are just the C0 gates. That's of course not true, but it's a first rough approximation. And secondly, we can also assume that noise acting on the C0 gate is depolarizing. This is definitely not true, but it's maybe the best, low-level approximation that you can apply. And what is still missing, even if you assume all these restrictive assumptions, we still don't know how strong is the error of the C0 gate. And so we have to guess it. And a good guess is basically to look at the device that you have. And sometimes this is reported. For example, the C0 error probability is given by this connection here. And you can also extract it in Python from the properties of the noisy backend. So in this case, we extract the gate error probability of the C0 gate between the qubits 0 and 1. And this is just a number that we can use as a very rough approximation of the noise acting on the C0 gate. And under all these assumptions, we can now build the optimal representation of the C0 gate as a linear combination of noisy gates. And this, in the case of depolarizing noise, is very easy. You can just use a built-in function from Mitiq and generate the operation representation. So you generate this object, which is the C0 rep variable, that is basically the Python object that represents this expression here. So you have the ideal operation, which is the C0 gate, which is equal to some coefficients times the noisy C0 gate minus some coefficients times the noisy C0 gate followed by a Pauli X, followed by Pauli Y, Pauli Z, and the same to the other qubit, and also 2 qubit Pauli errors applied after the C0 gate. This is the full quasi-probability representation of the C0 gate. under all the assumptions that we have seen before.
Yeah, I see, because you have a depolarizing noise, which is a form of a poly channel, and so you can decompose it this way. And if you had, if you didn't want to assume it's depolarizing, is there something you can do here, or?
Yes. So if you, well, you need, unless you know how to write down the quasi-probability distribution from theoretical arguments, maybe you have an analytical expression. For example, for amplitude damping, it is also known how to represent the gate. But in the most general scenario, you have only the noisy operator. So you have only the super operators of your gate set. So maybe you have a set of gates that you can apply with your hardware, and you have the super operators of those gates. And then what you can do, I won't do it now because it's a bit complicated, but you can import from Mitiq PEC representations, find, yes, optimal. I don't remember now. It's find optimal representation, something like this. I didn't get good suggestions here. But
I think you need a dot, yeah. That's okay, yeah, I guess.
Yeah, there is a function that basically, given the super operators of this, gives you the optimal representation.
Mm-hmm. Mm-hmm. And okay, I see. And it's on you to construct O sub a's?
The base, it's up to you, and usually, as I said before, a good guess is something like this, which you replace the same gate followed by other local gates, and sometimes it is very useful to add also a reset gate, because for example, for the amplitude damping channel, it can be shown that the reset gate is necessary to get a good representation. But it's still, yeah, it's true. It's up to you to choose the basis. Okay. If you want, we can explore a bit more this, but otherwise I will just try to run PEC with this set of representations. Actually, it's just the representation of the CNOT gate. And to run PEC, we decide how many circuits we want to probabilistically generate, in this case 100 circuits, and we decide how many shots per circuit we want to use. And since we want to compare with the unmitigated case, we distribute all the shots budget that we have equally among the 100 circuits that we generate. And for doing this, we define a new executor with a reduced number of shots, basically, that we call PEC executor. And so once we have this, we simply call the function PEC.execute with PEC that takes as input the circuit, the executor, and the quasi-probability representations, and the number of samples. And once we get this, we can compare the mitigated error and with the PEC error. Hopefully we get a reduced error when we apply PEC. So as you can see, this is taking a bit of time because what Mitiq is doing under the hood is to sample each gate of the circuit according to the representations and producing 100 versions of probabilistic circuits that will be the starting point for the application of PEC. After the circuits are generated, they are executed by the backend. And what you can see is that each time you execute a circuit, you use some budget of your shots, and most of the times the number of gates is the same, which in practice it means that most of the time you execute your input circuit, so the original circuit. But sometimes you apply one of those noisy operations that we have seen before, which is a CNOT gate followed by some Pauli gates, which means that the number of gates is slightly larger. So that's a simple way to detect when the circuit is changed. And in principle, by taking an average of all these circuit executions according to the rules of PEC, you can get a better estimation of the expectation value. And indeed, in this case, the error is reduced by 98%. So even under these very strong assumptions on the noise model. So basically, this concludes the idea of PEC. And I don't know how we are with time. I don't want to exceed too much. Maybe I can stop here.
There was actually, the next question was exactly how do you implement, well, from Amin, can you comment later on whether one can use Mitiq to implement the noise agnostic PEC introduced in PRA 107 blah? I think this is your paper.
Good. That's exactly this section.
So why don't you?
Of the notebook. So I'm happy to reply to this because that's a very new idea and still experimental. We actually don't know how scalable it is and how it works, but let's try to apply it. So the idea of NEPEC is that instead of assuming a noise model, you can try to build an operation representation, basically, a linear combination of gates that gives you the ideal gate that works even for different levels of the noise. So to do this, we define these two functions that actually we can skip because they are just details that are used to produce operation representations of this form. Let me show in a simple case. You decide a set of noise scale factors, for example, 1, 3, 5, and then you call this function represent operation with NEPEC. In this case, you want to represent the CNOT gate. And this is what you get. As you can see, it's very different from the representation that we had before. Before we had a CNOT gate written as a linear combination of a CNOT gate followed by Pauli operations. Here, instead, we are trying to express the ideal gate as a kind of Richardson extrapolation of the gate, evaluated at different level of noise. And in practice, how can we evaluate a gate at different levels of noise? Again, we can use unitary folding to scale the length of the circuit in order to have a larger effect of the noise. So in principle, this type of representation is exactly the same type of operations that you apply if you want to do zero noise extrapolation. You take a circuit, you scale it, and you take a linear combination of the results. The big difference here is that we are doing this locally at the level of an individual gate. And so we are actually, representing an ideal superoperator as a linear combination of channels, of quantum channels. I think this is the key idea. So if you have questions about this, feel free to ask. Otherwise, we can check. Yeah.
Why would this particular basis be a good basis to represent the gate n as a linear combination?
Exactly. So it's not maybe an optimal basis, but it's a way of expressing the ideal one as a linear combination of the same gate evaluated at different noise levels. And since it is based on an extrapolation, it works for different levels of the noise. So let's make a very simple example. Assume that you have no noise in the system. So zero noise. It means that this C0 gate is equal to a C0 gate because there is no noise, but also this one is equal to a C0 gate, and also this one is equal to a C0 gate because it's an odd number of gates. And so if you take now a linear combination of the same object, you get the ideal gate. So this representation works if you have zero noise in the system, but
So, 1/3, 1/3, 1/3.
Yeah, the choice of the coefficients, it depends on the scale factor. So if you have, for example, another scale factor here, 9, these coefficients will change, and they are exactly the same Richardson coefficients that you use to apply zero noise extrapolation. So you can think of this as extrapolating just a polynomial to the zero noise limit, but it's not a number, it's a gate. That's the key difference. We are not doing extrapolation of expectation values, but extrapolation of operators.
That's very interesting. So the 1.688 minus 0.75, those are the coefficients?
These are the coefficients, yes.
Mm-hmm.
These are just real numbers.
And how are they obtained again?
So they are exactly the same coefficient. They are obtained by this function, but I think I have to explain it. This is the function that you would use to extrapolate. Let me show this. To extrapolate here, this is Richardson extrapolation. So if you get 4 expectation values, in order to get the zero noise limit, you have to take a linear combination of these 4 expectation values. Basically, you fit a polynomial, and this number is a linear combination of this, this, and this, and this. This is called Richardson extrapolation. And now we take exactly the same coefficients because the coefficients depend only on the level of noise. That's an important aspect. It doesn't depend on the value of these expectation values. We take these coefficients and we use them to get the zero noise limit of the gate. So that's maybe not very clear. I think that the best way to understand this is to first understand how zero noise extrapolation works. And if one is convinced about how Richardson extrapolation works for expectation values, here you are essentially applying it for each matrix element of the superoperator.
And a quick question from the audience. So the results of noise agnostic PEC are biased. Is that right?
Yes. So this is an approximation of the ideal gate. It's not an exact decomposition. I agree, it's biased. But yeah, it's biased. But it's more robust to the ignorance of the noise model. That's the motivation behind it.
Sorry, what does more robust to the ignorance of the noise model behind it mean?
Yeah, so it means the following, that if you look, let me go back here. This representation that we used before is a representation that works only if the noise acting on these operations is a depolarizing noise of level C0 error probability. So there is a strong assumption on this one. In principle, it is exact, but as soon as the error model deviates from this, maybe the error probability is larger, maybe the noise is not depolarizing. If you have this representation is not true anymore, because if you execute this with a different backend, you don't get an exact identity anymore. So is this problem clear?
I think so. Yeah. I mean, here, if you if you let your coefficients be adjustable, you could do any poly noise model, but not anything larger than that.
Yeah, but it's not just this. It's that once you choose this, it means that you know how strong is the noise, right? This representation is a function of the noise model, and if you mischaracterize your noise model, this representation is not good, because you think the noise is something, but actually it's a bit more or a bit less or a bit different. On the other hand, since this is based on a extrapolation idea, it tends to work for different levels of the noise. And I don't know if this is convincing, but basically the coefficients of the Richardson extrapolation, maybe that's a way to explain it. These coefficients that you see here only depend on the noise scale factors that you choose. They are independent from the noise model. And of course, this is biased, but for example, if the noise is weak and if the noise is unknown, if you don't know how strong is the noise, these tend to be robust to mischaracterization of the noise model. Maybe I can also show a plot about this. I don't know. I don't think we have time. So there is a plot in the paper in which we show exactly this effect, this robustness to the mischaracterization of the noise.
Okay. Yeah. And is this a yes? I think maybe we see it at a high level, but might have to read the paper in more detail to understand exactly why this works.
Yeah, it's.
And I guess I should say how to what level of confidence has this been demonstrated to work or to work better? I think the question also actually asked from Amin was, can you compare this with typical zero noise extrapolation as well?
Yeah. So actually, we haven't done fully rigorous analysis of benchmarking different techniques. I think the only numerical experiments, have been done in the paper and in this notebook. So it's a very new technique, and we are looking forward to test this on hardware and to see which one is better and so on. In general, the motivation for this is that it's something intermediate between PEC and zero noise extrapolation. So zero noise extrapolation is biased, but can be very biased if the circuit, if the shape of the expectation value depends in a very nonlinear way on the noise, it can become very biased. PEC, on the opposite side, is unbiased, but it requires full knowledge of the noise model and so on. This is something intermediate. You try to do PEC without knowing too much about the noise model. So let me just mention another important point, which actually is the fact that if you want to use this representation, you have problems, because if you look at the one norm of this representation, is quite large, is 2.5, while the one norm of the previous representation is, where it is, here, 1.01. So it is extremely expensive to apply PEC using this representation here. So it turns out that the optimal way to reduce the norm and actually still to have good results is to have very large noise scale factors. So let's use just one and a very large number, like 101. This is a linear combination of the CNOT gate and a sequence of 100 CNOT gates, which in principle should generate more or less a random error, right?
Wait, I'm very confused though.
So basically, we are doing, it's like doing Richardson extrapolation with a scale factor of 101 for a single gate. It looks completely crazy, but the good thing of this is that you have a small one norm. And if you think about,
Can you motivate, so just intuitively, why does the one norm go down in this case?
Yeah, it's because you basically, it's like doing an extrapolation with a very large scale factor. And well, you have to look at the formula.
Yeah.
Usually these coefficients scale as 1 over the scale factor, something like this. And it's much, basically you can take a very small coefficient if you have a large scale factor.
Yeah, I guess my other just thinking is that usually with the Richardson extrapolation, at least with the pulse level extension, you usually work with pretty small scale factors also, because the noise swamps over your expectation values very quickly, and so you end up being in a noise floor, and then the inversion just goes wild due to the noise. So would that be this? I mean, it looks a little dangerous here to apply 101 gates, right?
I completely agree, but the point is here that we are doing something different. So this will happen with very low probability. So sometimes basically you add noise
That's
to the
true.
gate.
But that also means you need to sample a lot more, right? Because if you're not sampling this guy at all, then you're just applying the noise gate to begin with.
That's true, but basically you need, since this gate is more or less 0.1, with 100 samples, you will sample at least 5 or 6 times. And if you increase the number of samples, of course, you cannot take here 1 million.
Yeah.
Otherwise, it's a problem. And also, it gives you a bad extrapolation. So there is a problem with this. I just want to give you a justification why it's not so crazy to do this. And it's to think about what happens if you apply this. Basically, you can think of applying a CNOT gate followed by a random Pauli error, because for sure, probably here, some Pauli error will happen. And so we are trying to induce artificially an error in the gate with very high probability, because we are applying 100 gates. And if you look at this representation that we had before, what we are doing is applying with some probability the CNOT gate, and with very small probability the CNOT gate followed by errors. So in some sense, it's good that we are inducing errors by applying many times the same gate, because this is what you need in order to apply PEC. You need to take a linear combination of the gate with the gate followed by errors.
And how do I know my bias here won't be like completely dangerously off?
That's true. On the other hand, the noise probability for a single gate, it's quite small compared to a full circuit. So that's why we can still apply 100, maybe that's too much, but maybe 50 gates and still have an effect of the noise which is not extremely large. So it's biased, it's more biased because we are taking a large scale factor, but maybe we can still extrapolate to a reasonable limit because the noise is very weak. It's just a single, we are considering just a circuit made of a single gate. But I agree, it's a problem. It's a very crude, rough approximation. So I have no idea of what will be the results here, but let's see what happens if we try to run PEC with this very strange representation. And again, as before, we are generating a lot of circuits under the hood. And hopefully, this will happen in a reasonable amount of time, yes.
And meanwhile, folks, please post any final questions you may have. I've taken a lot of questions during the talk, and I know we're running 25 minutes over, which is totally fine because here we really tried to get deep and far, but we will be wrapping up right after this awesome demo.
Yeah, good. So just to finish this, as you can see, in this case, it seems to work. I have to say that more or less I choose this scale factor, checking which one was working better and not. So if I take, I don't know, 71, also works, but I had to play a little bit with this before giving this talk, but there is a regime in which it works.